Okay, in the last class we discussed about S is a state function and we proved that S entropy is a state function. We also proved Q is a path function. Then we discussed about change in entropy ds for isolated system is greater than 0 for spontaneous change and equals to 0 at equilibrium. Okay. By definition, all reversible processes are in equilibrium. So, ds system equals to 0 for a reversible process and greater than 0 for irreversible process or spontaneous process. Okay, but all systems are not like isolated systems. So, what would be the entropy change of system for not isolated systems? Okay. So, what would be the value of ds system for not isolated system? Next question is, okay. So, entropy change of system, so ds system consists of two components. One is called ds produced and ds exchange. So, what is ds produce then? Okay. So, ds produce is the entropy change by the process itself, and ds exchange is entropy change due to heat exchange between the system and surroundings. Okay. So, ds exchange is the entropy change due to heat exchange between the system and surroundings. So, ds exchange will be 0 when there is no heat exchange between the system and surroundings, and for isolated process ds system is nothing but ds produced, okay, because there is no heat exchange between the system and surroundings. Okay. Okay, so we can write, as we discussed, we can write ds system is ds produced plus DS exchange. Okay. Now, for a reversible process, we can write dq or del q, rather del q is nothing but del q reversible. Okay. And we just discussed that ds produced for reversible process is 0. Okay. Just we discuss this thing. So, what is ds exchange then? ds exchange is del q reversible by T, and this is this contribution from, this is from your, so you can write ds, this is nothing but ds system. Since ds produce is 0, so ds system is nothing but equals to ds exchange, which is nothing but equals to del q reversible by T. Now, for irreversible processes, okay, for irreversible processes, ds produced is greater than 0, just now we discussed, and ds exchange is nothing but del q irreversible by T. So, ds system equals to ds produced plus ds exchange, and if we substitute all these things, we can write ds system is greater than del q irreversible by T. Okay. So, what we got so far? We got for reversible process, ds system is nothing but del q reversible by T, and for irreversible process, we get ds system is greater than del q irreversible by T. Okay, so these things we have obtained so far. Okay, so next, now if we combine them, we get ds system is greater than equal to del q by T. Okay. And equal sign represents reversible process, and greater than sign refers to okay, and this whole thing, this thing you already studied. This is known as Clausius inequality. Okay. So, just now we discussed Clausius inequality. So, one thing we should remember is we must always devise a reversible process to calculate entropy change. Okay. For example, so we have a system which contains two bulbs like this, and we have bromine gas here, and this is vacuum, there is no gas here, and this is our initial state. And when you open the stopcock, the gas will spread, right? So we get the final state like this. Okay, this is bromine gas here and here. Okay, so this is our volume V1. This is nothing but V initial, and this is final volume. This is V2, nothing but V final. Okay, so V final consists of the volume or the sum of the volume of bulb 1 and bulb 2, and V1 is the initial volume, which is the volume of this bulb. Okay, so this is initial state, this is final state. Remember, if we remove the stopcock, gas will spread spontaneously. Okay, so this is an irreversible process, right? Okay, but how do we calculate the entropy change for this process? Okay, so we know, and suppose there is no temperature change. Okay, so no temperature change for this process. So we consider no temperature change for this process. Okay, as well as Br2 behaves ideally. Br2 gas behaves ideally. These are the two assumptions we are making here. Okay, so now we know ds is del q reversible by T, right? Since there is no temperature change for this process, so du equals to 0. Okay, no temperature change. As well as ideal gas condition. And ideal gas condition. Okay, so in that case, so del q reversible, we can write nothing but minus del w reversible, right? And we can write this is nothing but your nRT dV by V that we discussed before. Okay, so what we got? We got ds equals to del q reversible by T equals to nR dV by V. And if we integrate this, we get delta S, or we can do one more step here, like ds so we get delta S, which is nothing but S2 minus S1 is nR ln Vf V final by V initial. Okay. So we can calculate entropy change. Now what we did here, okay, although the process is irreversible one, but we considered process as if process is taking place reversibly. Why? Because S is a state function. Okay, so S is a state function. So entropy change from initial state. So, entropy change in the initial state. Okay, so we are moving from initial state, we are going from initial state to final state, and the process is actually taking place irreversibly, in irreversible manner. But since S is a state function which depends on the state of the system, means it depends on the value at initial state and the final state. So, basically what we are doing here, we are devising another path which is taking place reversibly. Okay, and we are calculating entropy change here. Okay, so this is how we can calculate entropy change. So far what we discussed is DS system is nothing but DS produced plus DS exchange. Okay, or we can write, if the change is finite one, we can write del S system nothing but del S produced plus del S exchange. Okay, and we know, we also discussed del S system for isolated processes, isolated system is 0. Okay, and del S system for not isolated system greater than equal to 0, and del S, okay, this one we will discuss later. Okay, so del S system for isolated processes or isolated system is greater than equal to 0, that we discussed so far. Okay. Now, we will consider different cases, like for isothermal reversible expansion, and what would be the entropy change for this process. Okay. So, we will consider ideal gas, and the process is isothermal one. So, delta U is 0. So, del Q reversible nothing but minus del W reversible. Okay. And we can write this one as nRT dV by V. And from here we can calculate delta S system is nR ln V2 by V1. Okay. So, delta S, this is delta S system. What about the surroundings? Delta is surroundings. Okay. So, if we consider system is gaining heat here, then surroundings is losing heat, same amount of heat here. Okay. So, delta S surroundings is nothing but your minus delta Q reversible here, and we can write minus nR ln V2 by V1, where V2 is our final volume and V1 is our initial value. Okay, so what about delta S total or delta S universe, right? You know, you studied those things. Okay, so delta S total, or we can write delta S universe is nothing but delta S system plus delta S surroundings. So, we can write this is 0. So, for isothermal reversible expansion, delta S total equals to delta S universe gives 0. Now, what about isothermal irreversible processes? Let us see. For irreversible isothermal expansion, what would be the entropy change? So, we can have two cases, right? One is your, so process is isothermal one. Again, if we consider ideal gas, since the process is isothermal one, we can write delta U is 0. So, depending on the work done, we will have entropy values. Okay. So, first case, the simplest case, case 1 is P external is 0, there is no external pressure like we discussed before. So, there is no external pressure for this process. So, what is your W irreversible or delta W irreversible minus P external time dV, this gives you 0. So, it says W irreversible is 0. Okay. So, it says no heat is delivered to the system by the surroundings. So, when external pressure is 0, so no heat is delivered to the system by the surroundings. So, there is no entropy change of the surroundings, right. So, delta S surroundings is 0, right. Now, what about delta S system? Okay. So, delta S system is nothing but your NR ln V2 by V1, right, because it is expansion process. Okay. So, system is producing some amount of entropy here, and that is your NR ln V2 by V1. Okay. So, what is your delta S total or delta S surroundings, okay, which is nothing but equal to NR ln V2 by V1. Okay. So, this is greater than 0 for expansion process. Now, what about the other case? Okay. The second case is when external pressure is not equal to 0. If external pressure is not equal to 0. Okay. Then, so we have here, think about like this. Okay. So, we have here initial state and we are going to final state. Okay. So, this is your irreversible process. But we are devising a path like the process is taking place in a reversible manner here, right. Since internal energy is a state function, we can write du is del q reversible plus del w reversible, right. If the process is taking place in reversible manner. If the process is taking place in irreversible manner, we can write du is del q irreversible plus del w irreversible, right. Okay. So, we can write from here TDS or DS system rather here plus del W reversible equals to del Q irreversible plus del W irreversible. And we can carry out the process we are not discussing here, and then we can end up with ds total is greater than 0. Okay, you have to apply here Clausius inequality, okay, and then only you will arrive at this expression. So, what we got so far? So, we got so far like for reversible isothermal expansion, delta S total, so delta S universe equals to 0, okay, and delta for irreversible process or irreversible isothermal expansion, for irreversible isothermal expansion, you get delta S total nothing but delta S universe is greater than 0. Okay. So, if we combine them, we get delta S universe, which is nothing but equals to delta S total is greater than or equal to 0. Okay. So, equal sign refers to reversible process and greater than sign refers to irreversible process. Now, we will consider different cases and we will see how we can calculate delta S system. So, we will calculate entropy change for ideal fixed mass closed system gas processes. Okay. So, first we will consider for an ideal gas at constant volume process. So, gas is ideal gas and process is a constant volume process. Okay. So, no PV work. So, constant volume process means no PV work, right. Okay. In that case, del W is 0, right. So, du is nothing but del Q. Okay. And if we consider this is reversible process, we can write like this. And what is du? We know du is nothing but your Cv dt. Okay. So, Cv dt and del Q is nothing but your Tds, right. So, we can write ds is Cv dt by T. And we can consider if we integrate this ds, we get Cv dt by T, temperature goes from T1 to T2. Okay. So, we can write delta S or S2 minus S1. If we consider Cv is independent of the temperature, then we can take Cv out, Cln T2 by T1. Here we consider number of moles is 1. Okay. If for n moles, we can write delta S is n Cv ln T2 by T1. Okay. So, we consider if we consider n equals to 1, we get delta S equals to, or here delta S system rather, we are considering system. Okay. So, delta S is Cv ln T2 by T1. For n number of moles, delta is n Cv ln T2 by T1. Now, this is at constant volume process. What about at constant pressure process? Next, we will consider for an ideal gas at constant pressure. Okay. So, ds is del Q reversible at constant pressure by T. Okay. And this is nothing but your n Cp dt by T, right. So, we get delta S is n Cp ln T2 by T1 for n number of moles, obviously. Okay. Third case, for an ideal gas and adiabatic process. This is the simplest one can think of, because adiabatic process means del Q is 0. So, it gives ds equals to 0 or del S equals to 0. So, nothing to do. Next, entropy change in terms of, next we will consider entropy change in terms of volume and temperature. Okay. So, we know del Q reversible is nothing but TdS, and del Q reversible is your del U minus del W reversible. So, we can write TdS du is nothing but Cv dt or ANCV dt for n moles, and this is nothing but your PdV, because del W reversible is minus PdV. So, we write TdS is NCV dt and P is nRT by V dV for ideal gas. Okay. So, we can write ds is NCV dt by T plus nR by V dV, and if we do the integration, we get temperature goes from T1 to T2 plus nR dV by V, volume goes from V1 to V2, and air entropy goes from S1 to S2. So, S2 to V2 minus S1 T1 V1 is NCV ln T2 by T1 plus nR ln V2 by V1. So, we get delta S is NCV ln T2 by T1 plus nR ln V2 by V1. So, this is the entropy change in terms of volume change and temperature change. Okay. Similarly, one can carry out entropy change, one can calculate entropy change in terms of pressure and temperature, and one can obtain delta S like this. Okay. And one can also get entropy change in terms of P and V. Okay. So, we get delta S, we can obtain delta S NCP, is very easy, V2 by V1 minus NCV ln V2 by